Okay, stereochemistry. It is on chapters 3 and 4 in this book. Alright. It actually goes into a bunch of different chapters also in this book, but 3 and 4, we'll deal with our stereochemistry. So if you're following along, looking for additional problems, that's where I would look. End of chapter 3, middle of chapter 3, and all of chapter 4, which deals with chirality. So stereochemistry essentially studies how atoms in a molecule are arranged in space relative to one another, meaning how are they bonded to one another, how do they spread out. Three different types of, or three different topics within stereochemistry that we are going to talk about. Geometric isomers, conformation change of molecules, and chirality of molecules. If you have a molecular model kit, okay, that could really help you for those of you who have a tough time visualizing 3D things. If you don't have one and you can afford like 15, 20 bucks, you can get them on Amazon Prime and have them at your house by the end of the week. Okay, so let's talk about a geometric isomer is based on rigidity, and rigidity can lead to forming isomers. Remember, isomers have the same molecular formula, but they might be bonded differently. So we talked about structural isomers where the bonding was different in last chapter. Geometric is how they are orientated in space. Conformation changes, the shape of the molecules can shift and move based on the bonding. And chirality is how many different carbons have four or more different things to it, and it's going to cause an arrangement, and we'll talk all about that in the future here. All right, so let's start with geometric isomers. So geometric isomers, all right, are based on a molecule if it has rigidity. Meaning, in order to have rigidity, I need at least a double bond, or I need to be cyclic. If I'm not a double bond or cyclic, all right, I don't have that rigidity. What it means is that the molecule could spin around a rigid axis, essentially. The molecules can move. Hence the term you see there, molecules are not static if there's rigidity. Static means they're stuck in a position. They're allowed to move around sigma bonds. So the pi bonds, or the cyclic compounds, allow my atoms to rotate around and move and not be stuck in place. Now the pi bonds then, when they get placed into a situation, and remember our pi bonds, our double and triple bonds are above and below the sigma bonds. Okay. This will allow movement around the sigma bonds, all right? But in order to do so, I'd have to break those pi bonds. So molecules are constantly moving. They're moving around those single bonds, those skeletal structures. The problem is, once I put a pi bond in, boom, that becomes a rigid structure. And in order to get that moving around again, I need to break those pi bonds to get back to those single bonds. Now, my molecules could continue to move, but they can't move with the same flexibility, especially those carbons that are doubly bonded. But the things attached may be able to move slightly, giving different orientations, and that's what it's saying here. The rigidity causes a fixed orientation for the atoms bonded to the sp2 hybridized carbons. So those atoms get stuck, and therefore we can't move them, and they're going to be stuck in a specific geometric position. And we see two here. Now these are the same molecule. And if we're going to go to our naming, it's 4 carbons in a row. So it's bute. Second carbon has double bond. So this is 2-butene or butuene, however you want to do it. But the orientation of these groups, all right, these CH3s here and here are different. All right, so we have a CH3 up here, and a CH3 up here, and a CH3 here, and a CH3 there. Okay, if they're on the same side, all right, of a double bond, they are known as cis-2-butene. Cis, same side, cis. The way I remembered it in school was sisters are close. Trans, they're on the opposite sides of the double bond. You need transportation to get across to connect them. Now, what I tell students all the time is this stuff out front is the cherry on the sundae. Okay, and what I mean by that is the important part to start is, can you name this 2-butene? Do that first. Then worry about cis and trans after. Cis-2-butene, trans-2-butene. Worry about that afterwards. So, still name it the way you would. Then see where the functional groups are to one another. Okay. These are known as stereoisomers. The reason they're known as stereoisomers or geometric isomers is the fact that their bonding is still the same, so they're not structural. But their orientation in space is different. If we take our 2D structure and show it in a 3D way, this is known as our configuration. The requirement for a geometric isomer is I need to be an alkene. It could also happen with a ring structure, but for us, our intents and purposes, we're going to focus on alkenes. There has to be a pi bond, and there has to be two different groups attached. So, to reiterate that, in order for cis and trans to exist, I need to have a double bonded carbon. If all of these are the same, there is no cis and trans. Okay? There is no cis and trans. They don't exist. If there's only one, there is no cis and trans. There's no cis and trans because it doesn't matter if chlorine's here or here, its partner is going to be hydrogen. In order for cis and trans to work, the carbon's in the pi bond. One of them has to be bonded to something different. This also has to be bonded to something different. Okay. So if I were to name this, all right, let's name it. I've got two carbons, so it's definitely ethene. I've got two chlorines, so if I want to, 1,2-dichloral. Chloro, ethene. And since they're across from one another, trans. So this is trans 1,2-dichloral ethene. But I need a double bond. I need two different things to be bonded in order for cis and trans or stereo or geometric isomer. Okay. Well, then arises the question, what if these two don't match? What if this is a bromine? What if I have three different? So is this trans or is these two? Is it cis? What do we do? Well, we can't use cis and trans then. Okay. If my carbons are bonded to 3 or 4 different things, like I show here, it's known as the EZ system, and it really is easy. All right. The E and the Z come from German words that E means across from and Z means together. The way, if you don't remember the German, obviously, enemies are away from each other. And that's the way I remembered E and Z, or I was told to remember it, and it kind of stuck. So if we have a compound like this down here in the right-hand corner, right, and we want to essentially figure out what notation we use, well, cis and trans is going to be tough to do. Okay, so we look at this, and well, is this cis? Is this trans? Do we have to call it like cis-chlorobromine, trans-chlorofluorine, or something like that? Well, no, we're going to use E and Z. But in order to do E and Z, we've got to assign priorities to each one of these functional groups. So let's talk about that. Okay, you look at each carbon and its functional group and rank them higher and lower by priority, and we'll talk about the priority rules. And we do the same over here, higher and lower. And then we could essentially use EZ. If the two higher priorities are across, that's E. And if they're next to each other, that's Z. And Gingen and Zusaman. All right. Well, how do I know my priorities? Well, here's how we rank them, right here. The substituents are ranked in order of decreasing atomic number on each carbon. The higher your atomic number, the higher your priority. Okay. The rules are based on, also known as CHIP rules, Kahn-Ingold Prelog system. And you might hear them as CHIP. And they were named after Kahn, Ingold, and Prelog. All right. So let's take a look. We got bromine and fluorine. We got chlorine and hydrogen. We're going to essentially split it up into two carbons and rank them by highest atomic number. So bromine is a higher atomic number than fluorine. Then come over here. Chlorine's higher than hydrogen. So this would be Z. Okay. You don't rank all four together. You rank them individually. So this would be, and that's an awful Z, so let's go like that so we can see it's a Z. Okay. So the complete name would be, and again, these are just toppings. Let's name it. It's ethene. We got it. You want to call this the one carbon? You want to call this the one carbon? I don't care. I'm not going to get into argument. Why is this the one carbon and not this one? Because B comes before C. That's really it. But if you called this 2 bromo, 2 fluoro, I'm okay with that. But so 1 bromo, 2 chloro, 1 fluoroethene. What if we have a tie? What if we have a tie? What do we do? Okay. If you guys ever played War, the card game, where if we both flip up a card, we then go to the next card. Or essentially you lay 3 down, or depending on how you play War, maybe you lay 1 down and you flip up the card, and then whoever wins the pile. Well, that's exactly what you do. So let's say we have this. We have a carbon bond to a carbon. Let's say there's a hydrogen and a bromine over here. But over here, we have a CH2, CH3 group. And over here, we have a CH3 group. And we want to rank these. Well, I know this is higher and this is lower by atomic number. And we come over here. Well, carbon and carbon. That's a tie. Okay? So we go to the next thing. A hydrogen, tie. A hydrogen, another hydrogen, tie. A third hydrogen and a carbon. Our third tiebreaker gets a carbon versus a hydrogen. This carbon's higher atomic number than this third hydrogen. So this would be the high, this would be the low. These are across from each other. This would be E. Now, if we want to worry about our full naming here, okay, let's call this 1, let's call this 2. It's still ethene. Oh, it's not ethene, sorry. I'll be okay. So 1, 2, and let's see, our longest is 3, 4. It's 1 butene. Okay. And yes, I snorted there. I don't know why. We got a bromo on 1. We got a methyl on 2. So 1 bromo, 2 methyl, 1 butene. And the little cherry on the sundae is an E right there. So our complete name would be E, 1 bromo, 2 methyl, 1 butene. And that would essentially say, well, I have butene. I have a methyl on the second carbon. I have a bromo on the third carbon. Or on the first carbon, I should say. And those groups, based on the rigidity of the alkene, cause them to be across from one another. Okay. Questions on this so far? Questions on this so far? Okay. So, let's get into it a little bit more. We got our group, and I'm just going to focus on one side here. Let's say we have a carbon bonded to a carbon, bonded to a carbon, bonded to a hydrogen, like so. And the group off of here, all right, is carbon bonded to a carbon, bonded to a carbon, and these are all bonded to hydrogens like they should. Now, this might be written, just so you guys could see this, and these are going to be hydrogens, by the way. It might be written something like this. Another way of writing what I have up here, this top half, you might see it written as CH2, parentheses, CH3, 2. That means that, or sorry, CH3, 2. That means that each other bond that carbon needs is a CH3 group, and this down here would be CH2, CH3, CH3. All right. Or CH2, I should say. CH2, CH2, CH3. Like so. All right, well, I want to assign high and low priority here. They're both carbons. They both have a hydrogen. This one has a second hydrogen. This one has a carbon. So this is the higher priority. Okay. So again, you're playing the game and working your way down, and whichever one ends up with the higher priority or higher atomic number takes priority. So, that being said, let's imagine we had this. Okay. I've got a carbon that's bonded to a carbon that's bonded to a carbon that's bonded to an OH. That way. I have a carbon that is bonded to a hydrogen that's double bonded to an oxygen. I have something that looks like that, let's say. Now this would also be bonded to an H and another H just for fun. And to complete the octet. And we want to assign high and low priority. If I have something double bonded, we treat that as the following when we're doing chip rules. We would treat that like this. That double bond would mean I'm bonded to 2 oxygens. So if I were doing the rules, I would say this carbon down here is bonded to a hydrogen, so am I. It's also bonded to an oxygen. So am I. But I'm also I'm double bonded, so I'm really bonded to a second oxygen. Oh, I'm bonded to a hydrogen. That's the winner. Okay. So you just keep taking it out further and further until you find a difference. All right. If there is no difference, then you can't have EZ or cis-trans for that matter. Okay. And the examples in the slides do that for you. The examples in the slides go over all of that. Chip rules here. I mean, look at this one. Gets kind of complicated, but don't panic. All right, we want to outrank and show and do all that, and I look at this on an exam and I'm like, oh my God, what is this? Break it down. What do you got here? Okay, and if you can't see it as the line, or as the skeletal, draw it out as the line. I've got a carbon bonded to a carbon, so do I. That carbon is bonded to 2 hydrogens and a carbon. This carbon's bonded to 2 carbons and a hydrogen. Carbon, carbon, hydrogen. So this is the winner. Okay, so if I'm looking at this, this is the higher side. Why is this the higher side? The first carbon in is bonded to 2 hydrogens. This carbon's bonded to 1 hydrogen and 2 carbons. So that's going to win. Okay, let's go over here. Carbon to 2 hydrogens. Carbon to 2 hydrogens. All right, move to the next. Carbon to 2 hydrogens. Carbon to 1 hydrogen and 2 carbons. Boom. Winner. Right there. So, this is the higher side. And this should be the higher side as long as I'm looking at it right. And since they are next to one another, this would be Z configuration. Now, if these were both, let's say, hydrogens, this was a hydrogen, this was a hydrogen, that's when we would use cis and trans. It's when there's 3 or 4 different groups across the double bonds, then that's when we have to get into E and Z. Okay. All right. How about something like this? I don't care if carbon's bonded to 3 carbons. Oxygen has a higher atomic number. Even though it's carbon bonded to essentially an oxygen and 2 other hydrogens, and those 2 carbons here, these 2 carbons, right, beat these 2 hydrogens. They're winning. However, oxygen wins. Oxygen takes precedent over that carbon, so this side is higher. It's not the total that you have. All you need is that one card. So like I said, War, all right, is the best example, the card game War, if you've ever played it, in my mind. Last time I brought that up, though, the majority of students looked at me like I was crazy, like they never played War. So I don't know, maybe I'm just that old, all right? If you did play War before, if you could type in the chat to make me feel better about myself, that'd be awesome. Here's the double bonded thing that I was discussing. And you do the same for a triple. All right, you do the same for a triple. You treat it as 2 individual bonds to an oxygen. Okay. So, are there questions about cis, trans, EZ? Again, these are geometric isomers. Stereoisomers. Cis and trans are stereo. E and Z would be stereo of one another. So E with some name is a stereoisomer of Z because all it means is I have the same bonding. So this isn't like when we looked at, ethanol and dimethyl ether. Okay, those are 2 different compounds. Those are structural. These are just, hey, I'm a little bit different in space. Okay. All right. So before I get into Newman projections and talk about it, let's talk about drawing our structures out. And I'm hoping it's a review from Gen Chem, but if not, okay, we'll learn it today. We draw our structures out in such a way that when we draw them out, I don't care, chlorine and bromine. Okay, we draw them out in such a way that they're represented as a 2D structure. But we know that when we start making bonds via our geometry and our hybridization, we know that this should be a tetrahedral. Okay? So we know it should have a 3D shape. All right? The wedge and dash method lets us show that 3D tetrahedral. If I'm an sp3 carbon and form that tetrahedral, one of these components is going to be coming out at me, and we represent that by a wedge, a triangular wedge with a square base coming out, filled in. That means it's coming out. We'll put the bromine there. A dash means I'm going back into the board. A line means I'm in the plane. And it doesn't matter how you align it right now. To show 3D structure. Okay. This is known as the wedge and dash method to show 3D structure. Now, that being said, we're going to look at something called Newman projections. And what a Newman projection does, so let's say we're drawing a carbon chain out, like so. Okay. And I don't care. Let's just put some hydrogens there. We'll put a chlorine on there like so, just to watch. And let's do, I don't know, a fluorine here. Sound good? And let's do 3 hydrogens back here. So we're looking at this, put a hydrogen in. We're looking at this from a side view of the chain. And my molecular model kit, I definitely thought we would be back in by the summer. So I didn't bring my molecular model kit home, and I'm kind of ticked off that I didn't think about it. But we're looking at this, all right, molecule from a side view. Now we know this is a 3D shape, even though it's real thin. We know this is 3D. We're looking at the molecule this way. But what if I wanted to look at it like this? Straight down the chain. I wanted to look at it. Here we go with my beautiful I don't even know how to, I don't even know what I'm trying to draw here. I can't draw. How do you draw an eye looking this way? That's an eye looking that way. It looks like I don't even know what that looks like. Do I put eyelashes on it like that? I have no idea. But that's an eye. That's a person. Let's make that their nose maybe there. We'll do that. There we go. We're a person looking that way. Okay? Down the chain. We want to look at it that way. And that's what's known as a Newman projection. All right, a Newman projection will essentially show that. And they're really easy to draw. You're going to draw 2 carbons essentially. Just try and find my mouse. It disappeared on me. There you are, mouse. All right. And it's going to show essentially what is the best way for our carbon molecule chain to have itself rearranged down, looking down the chain. So here's how it works, okay? And what we're really looking at something called torsional strain or torsional repulsion, all right, between our molecules. Now, I am not going to get super complicated with Newman projections, especially since we're dealing with them online. I'm not going to deal with them doing double bonds and things like that. We're going to look at them singly bonded and looking at them only singly bonded. Okay? So, here we go. You pick 2 carbons in the chain. Which way are we going to look? Okay, so we're going to look at these 2. So we're going to represent these 2. Okay? We're looking at, and I'll even star them for you. All right. We're going to look at these 2. And here's how you do a Newman projection. Very simple. All right. Very simple, straightforward. We are ready to roll. Okay. Draw a circle. Like so. That represents the second carbon. The circle is literally the carbon. And there's a dot. Okay, so this carbon is the dot. This carbon is the circle. Now, fill in what's on this. I have a hydrogen. I have a hydrogen. And I have a chlorine. Fill in what's on the circle. I have a hydrogen. I have a fluorine. And I have a methyl group. And that is your Newman projection for here. Now, I want to draw the next one. I would look down these 2, and so on and so forth. Okay? Now, so what? What is this really showing? Is this the way this would really sit? What's another way it might sit? Okay, another way this same molecule at this same view might sit is the following. Chlorine might be up here with the hydrogens down here. Let's move those. But how about if we move the methyl group over here and we move the hydrogen over there, and we do kind of like a turn of this without moving the middle, and we put a fluorine there. That's possible. And what's even more possible, another possibility that we might not think of, is do this, put the chlorine. I'm not going to move the chlorine or the hydrogens. They could move too, though. Okay? But just for, I mean, there's multiple ways to draw on this. I could also have, who knows, the fluorine right there next to it. And right down here, I could have the CH3. And right down here, I could have the other hydrogen. Okay? These where, apparently I'm going through puberty. Whoa, voice cracking. These here, that they're not lined up next to each other, they're kind of spaced out, is known as the staggered form. These here are known as the eclipse. Now, the eclipse form, due to repulsion and torsional strain put on the molecule, is the least likely to happen and have the highest amount of energy. We don't want that. Okay? And on the slides, they use just plain old everyday ethane, and not something like a little bit more complicated that I drew, and just show you that if the hydrogens are staggered, then they are better off than if they are eclipsed. My energy starts to go up. And if you remember, when a molecule forms, the purpose of said molecule to form is to lower my amount of energy. So we want to lower our energy. We don't want to increase our energy. We want to lower our energy. So what form are we going to take? Well, here is butane. And here's 4 different ways of showing butane. We have eclipsed, where the 2 methyl groups are next to each other. We have staggered. We have eclipsed again, where a methyl is near a hydrogen. And then we have staggered one more time, where the methyls are across from each other. So if I were to number these, 1, 2, 3, and 4, which one of these is the least amount of energy and which one is the most, do you think? Which one is the least amount of energy and which one's the most? if ideally butane was sitting there and we were looking at essentially, this would be what, the second and third carbon? Yeah, the second and third carbon we would be looking down right now. Because here's carbon 1, here's carbon 2, here's carbon 3, here's carbon 4. What carbon would be the least energetic? Which formation? Yep, Keith, you are 100% right. 4 would be the least, and 1 would be the most. 4 would be the least because my methyl groups are in the the staggered form and away from each other. While this would be the most because it's in the eclipse form and the methyl groups next to each other. This staggered, not as good as this one because these two are near each other, causing some strain and resistance. And again, these are eclipsed and we don't like that. So let's go back over here to our live blackboard here. And which one of these? You know, I got a staggered here. Okay, so eclipsed is out. This is definitely out with a chlorine and a fluorine next to each other. Blah, we don't want that. Well, how about this one versus this one? Well, if I had a guess and I'm looking at it, although fluorine is very small and chlorine small, and do I want a bulky methyl group? I don't know. I'd have to really look it up, but I'm thinking that the electronegativity of chlorine and fluorine are going to be so strong to resist each other that this might put more strain on it than a bulky CH3, a more bulky CH3 group in a chlorine, and keep those halogens away from each other. So if I were guessing without looking up any numbers per se, I would say that this is better energy-wise than that this is. And this is just awful due to the fact that it's in the eclipsed form. Okay. Are we okay with that? And if we're okay with that, then there's another term that goes in here. Well, how do I tell the staggered away from each other? If the main functional groups are away from each other, the ones with the highest numbers. So that's why I'm thinking the fluorine and the chlorine also, if we're following Chip's rules, the fluorine and chlorine are higher atomic numbers, even though that's a CH3 group. So they should be separate from each other. If the numbers or the functional groups are across from each other, we call that the anti-conformation in the Newman projections. So in our case, this would be anti-butane. While this would be gauche. They're in the staggered form, but the main functional groups are next to each other. So whether the CH3 was here or here, if they're next to each other, they call that the gauche form. So if we go back here and we call these, this would be the anti form right here, and this would be the gauche form. If we were naming this, of course, this is propane. Okay. 1 chloral, 2 fluoral propane. This method would be gauche, 1 chloral, 2 fluoral propane, and this would be anti, 1 chloral, 2 fluoral propane. Again, name your compound first. Worry about getting the name down before we start adding all the flavor. As you know, I'm a fat guy, so that's why I use toppings on the sundae and the flavor. That's how I roll. All right, let's talk about one more topic today, and that is our beautiful cyclohexane. So we draw cyclohexane on the board. If I drew a 6-member ring on the board, and you're always going to draw it like this, you're even going to draw it when we start drawing out 1,3,5 cyclohexene, which is also known as benzene. If I asked you to draw a 6-member ring right now, we all go to that drawing we always see. Boom, 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 and boom. This is cyclohexane. The problem is, cyclohexane really doesn't sit like that. If cyclohexane sat like that, there'd be too much angle strain on there, And I know it's not great. I'm terrible at them. That's one of my better ones usually. I had a student a couple of years ago just kept ripping on me. Actually bought me one of those notebooks that already has the benzenes in, and you just have to trace them because she said it was so terrible. So, yeah. But cyclohexene really doesn't sit like that. Hexane doesn't sit like that. It really takes on different conformations and moves to not only limit torsional strain, but to also, it's kind of like Vesper theory. Not exactly, but it wants to spread out the best it can so there's the least amount of repulsion and the least amount of tension placed on the bond of said molecules, or atoms in that matter. So we have the chair conformation where the carbons kind of spread out. We dip in and we get something that looks like this. And it's called a chair because you could put a little person in there. Okay, so we'll just draw our... I always picture them laying this way, but however you want to. There's our person laying in the chair. Put a little pillow there for them. All right. And we also have the boat. So we'll just put a little flag here for our boat. And those are two conformations that our cyclohexane could sit in. And they transition from boat to chair and chair to boat and everything like that. Well, which one is the most stable? Well, let's talk about it. Here is the conversion, or as they call it, interconversion of the conformations, going from chair to boat to chair, and so on. And it's more like, and I pictured it like origami when I was in class. The chair folding to become the boat unfolding to come back to the chair. The chair has the least amount of torsional strain. Has the least amount of repulsion, and therefore is the lowest energy. The transition from the chair to the boat requires energy. If the energy is available, it will do this. It'll also go right back to the chair to have the lowest energy. So I have a student ask me, why does it do it if it's of higher energy? Hey, if the energy is available and the bonds want to move around and they have that ability, since it's all single bonded, but there is that rigidity due to the cyclic structure, they'll still try to fold and move. Because the molecules and the atoms, they aren't static, they're constantly moving. That's what's keeping them bonded together. I mean, that's why at absolute zero, all physics and everything breaks, all hell breaks loose. Because at absolute zeros, our molecules stop moving and vibrating, and therefore our bonds don't exist. So if there's enough energy available in the environment, the cyclohexane will constantly move and absorb that energy and go into that boat form, even though it's of higher energy, but it'd rather be in the chair. The chair has less strain placed on the ring structure. The worst structure, actually, out of all of them, is the way we normally draw it and represent it. That's not good at all because these are all sp2 carbons. So they should all be in a semi-trigonal planar way. This is a carbon. There's two hydrogens there. Bonded to a carbon, or sorry, an sp3. I think it's an sp2. But they should all be in a tetrahedral way. I might even said trigonal planar there. It's getting late. Tetrahedral way. You got 1, 2, 3. They're all sp3s. So they want to be in that tetrahedral way. They don't want to be in this way at all. That's awful for them. Okay. Now, my hydrogens can line up around this chair form, and they could be known as the axial position, where they're all faced towards the outside. Okay, again, you have to kind of picture this as 3D. So this hydrogen right here, okay, this hydrogen right here, and this one right here. If we're picturing this as kind of 3D, all right, that one's coming down like this, and this one's coming up like that. So the one pointing upwards is coming out of the chair. Okay. just so you could see that. We also have the equatorial position, which they're all lined up like so along the outside, as you can see. Like so, not pointing upwards, not pointing straight down, not pointing straight up, not pointing straight down, kind of laying with the plane of the molecule. Equatorial position. Okay. Now, so there's two ways for my hydrogens to line up to try to separate and be far apart from one another. Let's talk again about our strain that's placed on our molecules, okay? We talked about if I have multiple carbons, eclipsing strain versus the staggered. Okay, so eclipsing, they're right next to each other, not good. That's strain, that's overlap. Steric strain, crowding of the atoms in the molecules. Our steric strain was, the two methyl groups next to each other, the chlorine and fluorine next to each other. We don't want that. And finally, angular strain. All right, our angle strain is if I'm an sp3 carbon, I want to be 109.5. Well, that ring structure is not letting me be 109.5. Okay, so we don't like that. We don't want that. So let's take a look at the strain in cyclohexane on those three principles. Here is the planar structure that we always draw it out. Now they're drawing it horizontal instead of vertical, but still, we have a problem. The way this is drawn, we've got 120 angle. We want to be 109.5, strain number 1. Number 2, I've got eclipsing of all my hydrogens next to each other and all of that. The carbons are interfering with one another. We don't like that. Increase it. Steric strain, there's not so much. They're hydrogens. They're kind of distance from one another, but there is some. All right, let's move to that boat structure. Boat. The angle strain, hey, we're getting more to 109.5 if I make that boat structure. And if you have to, fold a piece of paper, look at it if you don't have molecular models. Problem, I have eclipsing occurring. So there's problem there. I've got a whole bunch of hydrogens near each other. We don't like that. That's steric crowding. Twisted boat stinks. We're not even going to look at all that. There are some small eclipse strain, but this is why it's a little bit better than boat, but not as good as chair. Slight angle strain, some eclipsing, some steric. But now we get to the beauty. Right there, the winner. Boat. No angle strain. Why? Because my carbons in this form, chair. The carbons in the chair form are 109.5. There's no eclipsing. The carbons are getting out of the way of each other. This is out of the way of this one. This one's out of the way of that one. This carbon's out of the way of this one. So we're not really getting any eclipsing strain. And the hydrogens might be a little bit close. So at worst, we have a small steric strain. So if you were asked in a multiple choice exam sometime in June about which conformation you would like to follow or something like that, the chair conformation is the one our cyclohexane would like to be in for the following reasons. Okay. And this shows it. Now, this is a really detailed Newman structure showing ring structures and things like that. Again, due to time, due to that, I need to discuss Newman structures with you. I need you to be able to look at them, but I will not be asking you to show me ring structures and how they interact. I'm going to be asking you about Newman projections based on looking down the line like we just did in the examples and in the slides that don't detail this here. Okay. All right, that's where I want to stop today. And I want to ask, do you guys have any questions? Now, there's 7 of you watching currently. There was 8. So this is all Chapter 3, Chapter 4 stuff in the book, if you need to follow along. I do want to talk to you about your exam, so if you are in the chat and listening, if you could sign in and talk to me here. So tomorrow is supposed to be your exam. on nomenclature and on the Chapter 1 review stuff from Gen Chem. My question to you is, do you still want to have it tomorrow? Or would you rather have it on Thursday, me record a lecture so that we don't have lecture and the exam, but we could still have it on that Thursday when we're supposed to meet, and I will have a recorded lecture that you'll be responsible for watching? That is my question for you. Do you want the exam tomorrow? Chapter 1 and Chapter 2. Essentially, nomenclature and all that unsaturation stuff, all the hybridization stuff, all the Lewis stuff, the acid-base stuff, all of that will be on the exam. So, do you want it tomorrow? Do you want it Thursday? If I gave it on Thursday, you could take it any time on Thursday, but we would not have a live lecture. I would record a lecture, and you would be responsible for the material on the recorded lecture, which would be chirality. Either way, I'm already making up the exam and getting it up on Blackboard, but I just want to know what you guys want to do. I run a semi-democracy here. So that's why I'm saying the 7 of you that are in the chat live, of the 12 people that are signed up for the class, you are a majority. So if I get a majority vote, we could have it on Thursday if that's what you want. All right, I have one say stick with tomorrow. I have one say Thursday. I got another one that says Thursday with a recorded lecture. That's 2. I don't care either way. I'm making up the exams tonight. So, I got a big night, very exciting here. I got to make up a Gen Chem 1 and an Orgo 1 exam. So I got 2 Thursdays and 1 Wednesday. That's 3 votes. It'll be there Thursday from like 8 a.m. till, let's say, 8 p.m. I don't know, 30 to 50 multiple choices. I didn't work them up yet. I started penciling questions down that I was thinking about. That's what I meant by I'm already starting putting it together. Yeah, so the 3 PowerPoints plus the nomenclature, Madison, if we did it on Thursday. Or if we did it tomorrow, it's the same thing. The difference is if you did it tomorrow, we'd have a live lecture. I would be there live. But if we do it on Thursday, I don't want you to have to take the exam and come to lecture and get all that, which you don't technically have to. I would let you take the exam on Thursday and have this lecture posted. I don't care either. Like I said, I'm making the exam up tonight. It'll be done and ready to roll. If I could cover all the material in 30 questions, then yes, it will. It might be even less than 30. I don't know. I'm not going to sit there and make up longer questions than whatever. I just like to do a number where if you get a couple of them wrong, it doesn't kill you. Like, I could technically do it in 10 questions. But you get one wrong and you're already down to a 90. So the reason I like 50 is the fact that if you get a couple wrong, it's 2 points off. I could tell you're all paranoid. All right, so Thursday, are we cool with Thursday? So that's what I'm going to write on the board here so that anybody who didn't show up watches the video here. So Thursday would be what? The 18th. So exam on Thursday, The material is the nomenclature in the first set of PowerPoints. 6, 16, 20. Blackboard. It'll be under the assignments. It'll be under assignments on Blackboard. Okay, so Blackboard under the assignments. Let's say it'll be available from 8 a.m. to 8 p.m. Once you log in, you can't log out. Once you start the exam, you can't not finish it. It'll automatically close. I'll give you about 2 hours to do it, an hour and a half. Oh, 6/18. Today's the 16th. Yes, 6/18. Good call. 6/18. I'll give you an hour and a half to 2 hours, okay, to do it. All right. I mean, if I do 30 questions, KK, if I do 30 questions at 120 minutes, that's 4 minutes a question. So I'll probably do about 90 minutes, which gives you about 3 minutes per question. That's an hour and a half, because my exams are usually geared for, lecture time, an hour and a half. And then there'll be a video posted on YouTube of the lecture we would have had on Thursday. You can still email me questions and everything. That's fine as a review on Wednesday, tomorrow.